Example 2, we have the area bounded by y equals 5. So I've shown the line y equals 5 here. And by the green parabola x squared plus 1. So that area is this yellow area. Now, in this case, what we're going to do is we're going to rotate this around the line y equals 5. Okay, so it's going to be rotated around the line y equals 5 around here. So that yellow area, when we rotate, it's going to generate this shape. Okay, so taking a look at that shape, it's going to be kind of like a disc, and every slice is going to be a circle. So we're going to use pi r squared for this. Now, what's important though is we need to make sure we can establish the radius of this circle. So we have this circle that we're going to generate. I'm just going to draw it like this. Okay, so there's our circle. And the radius of this circle is going to be the distance from here to here. Okay, that's our radius. Now that distance is not f of x. Okay, that distance is the difference between the line y equals 5 and the f of x function. So that radius is a difference of two things. So we have to express that as a difference. A distance on a coordinate plane is always a difference. So that radius is going to be the difference between, and that's going to be the same as that, is going to be the upper bound, which is y equals 5, minus the lower bound, which is that parabola, x squared plus 5. Okay, make sure you put that in brackets. So in simplified form, the radius is going to be written as 4 minus x squared. Okay, so that's going to be r equals 4 minus x squared. Now that's important because we need to use a difference of those lengths to work out the radius. Now we can use the radius to work out the area of the circle. So that circle now, that circle here, this area we need to work out. So the area of that circle, the expression for the area of the circle is going to be pi r squared. Pi r squared. Now in this case, the r works out to be the difference between the height of the line y equals 5 and the height of the line y equals x squared minus or x squared plus 1, which simplified to 4 minus x squared, and we're going to square all that. So that's the key. We want to find the area of the cross-sectional slice. So you can imagine as we rotate it and generate this solid, I've only rotated kind of 3/4 of the way, but if you imagine it rotating all the way and you slice it along perpendicular to the x-axis, or the perpendicular to the line y equals 5, we're going to generate circular discs, and every slice is going to be a circle. So then working out the volume of this object, the volume is going to be, we take the area, pi r squared, and we're going to integrate that from our bounds. Well, it intersects that line y equals 5 at x equals -2 all the way to +2. We're going to give it some thickness of dx. Okay, so every slice here, if we imagine each slice is going to have a thickness of dx. So then we're going to add those all up, or in other words, integrate it, and we're going to get the volume of this object. So first thing is I'm going to expand this out. Okay, and again, we don't want to integrate this expression as is because there is an embedded function of x squared in there. We cannot use power rule at this point. We have to expand this out. Now we can anti-differentiate this. So volume is equal to pi 16x minus 8x cubed over 3 plus x to the power 5 over 5. And we're going to do that from -2 to +2. Okay, so plugging this in, we end up with 32 minus, that becomes 64 over 3 plus 32 over 5, and then we're going to subtract this exact opposite, which means essentially we're going to double that value. Okay, so when we work that all out, that's going to end up being 64. So let's just type that into our calculator. So we get 32 minus 64 over 3 plus 32 over 5. And that's going to give us the fraction 256 over 15. And then we're going to double that. So we end up with 512 pi over 15. And that's going to give us the volume of units cubed.